This is one of the final step in the physical design term. So post after the CTS can also call as post CTS. The next step is called routing. So which already you heard about the routing. Okay, first routing. What is meant by routing, and what you've seen before and what you're going to see now. Okay, routing is nothing but it's a process of creating physical connection among your among the signal pins of your cell or or any hard macro by following some design rule checks which was provided in your technology file as per your nanometer technology or nanometer. So I'm just repeating again. Routing is a stage where you're going to provide physical connection. Just let me draw that one. There is a cell here. There is a cell here. Okay. Let me draw like this only. So till CTS, you don't see signal routes. We have three types of routings. I will let you know first. So now this is a one cell. This cell may be either flow or any logical cell or macro. So the connection, so there are a lot of pins here. There are some input pins and there are some output pins. And the same for this cell. And same outputs, some different outputs there. So the connection, the physical connection of the pin of this cell is connected to the other input pin of other cell. So this is called route. Okay. So if it is a if the pins are related to signal nothing but think that now it's an AND gate. You all already know, right? AND have two inputs. So these two inputs A and B is called input signal pins and C is called output signal pin. So output of one logic is connected as input to the other cell. So if it is a signal related, that is called signal pins. If I say, if I take a flop and if I take one more flop, there is a clock pin, which you are aware. So the connecting of these two clocks by means of some route is called clock route. So first routing is process of creating a physical connection between the pins of a logical cell based on some design rule checks. So these design rule checks are defined in your tech file. So this tech file is based on your nanometer. Which technology you are going to use? Based on the technology. So this width should be this much. The spacing should be this much. So suppose one metal is here and some metal is it is coming like this. The spacing between these two metals, width between the two metals, pitch between the two metals. This was decided by using design rule checks. Okay, we can call it as short form DRC. Okay, so why we are going to concentrate this proper routing? So after routing, so your timing and the condition has to meet. So this is a main criteria about routing. So generally, before to route, we saw CTS. CTS is meant for clock pre-synthesis, where the clock has been physically connected. So before that CTS, you have placement. Before to the placement, you are going for flow plan. In flow planning, I mean to say chip planning, there is a term called power plan. So first, coming to the types of routing, I don't know, I didn't capture, I think. Okay, I didn't catch it. Generally, you just listen. Coming to usually the routings are classified into three different ways. So one is clock routing, one is signal routing, and one is the power routing. Power routing is also called as pre-routing, okay, which comes under power plant. So all standard cells has to get power. So we are going to route power plant with the higher letters and next higher metal layers. And the next is clock routing. So clock routing you can see during the building of the clock. So building of the clock takes place in CTS stage. And then, so once CTS has been, once standard cells has been placed, then so the flops will get routed by using clock routing through CTS engine. And the next step is called routing. Here the routing is called signal routing. It is after CTS and it can be said say as just routing. Okay, hope you understand that. So this I didn't capture here. If you see, there are three routes. PG route, nothing but power or pre-route, clock route, and signal route. Okay, coming to the so everything have some inputs and outputs. So first, let me explain you what are inputs required. So first thing, when you look for a PD flow, there are multiple steps defined. Okay, suppose if you are going to if you are going for this step, so you are getting input from the previous step. So coming to the route as well, when the if you are going, they think that this is a route state, the before step is CTS. So you need CTS def as an input when you are going for the route stage. And similarly, the basic inputs required is called CTS def or CTS database, or where the clock get routed, we are going to save the design. That design is called CTS def. And the next one is called netlist. So netlist, timing library, physical library, tech life, and RC table are all are the common inputs required for each and every stage post after the placement. Okay, and SDC. SDC nothing but synopsis design constraint. Or you can say that, okay, you just remember synopsis design constraint only. Okay, and coming to the output of the def. So once your output is finished, routing is finished, then it will get some, it will release some output. That is called route def. If you see CTS, the output is CTS def. If you go for the placement, the output from the placement is placement def. If you go for the flow plan, output is flow plan def. The same way, route output is route def. And there are some other timing reports also it will generate. Okay, you have to go and open the, go into that particular directory. It will create multiple reports based on your scenarios and corners defined and based on some constraints. So you will find many reports. So required reports you have to go and open. And once you open that, you have to check whether you are routing or some simple, because of routing. So is this timing report is showing any setup or hold violation, or you can say that timing has to meet or not, or it has met or not, you have to check. And there also some other reports related to the congestion, that also you have to go and check. So generally congestion, we is going to call it as a hotspot. If more number of cells are sitting in this area, I can call this as hotspot. Okay, so these are inputs and these are outputs required for the or from the routing. Coming to the goals, for each and every stage, you have input and output. Similarly, you have some targets and goals. Coming to the goals of routing, so it has to route all your standard cells in proper way. So think that in my design, I have 10 millions of logical cells. So each and every logical cell has to routed by using in, connections which is provided in the netlist. So route all signalets with minimal DRCs. DRC is nothing but one net. So there is one cell, there is one more cell here, there is one more cell here. Think that there is one more cell here. Think 1, 2, 3, 4. So generally 1 and 2 are connected and 3 and 4 are connected. So when this connection is happening, so they may get a shorts, I mean the wire which is or the metal which is connecting the cell 3 and 4 should not short with the connection between 1 and 2. So this is called physical dialysis. It should not have any short. It has to follow some width, some metal height, some anything, someone mute. Sai, Sham, you need anything? Water, drink the water. Okay. So 1 and 2 has to connect, 3 and 4 has to connect. So this has to be avoid some DRCs, design rule checks, and it should not get any shorts and opens. Nothing but 3 and 4 has to connect. If it is not connected, these two set to be open or signal. Yeah.
Share the PPT.
Can you check now?
Okay, ma'am.
Yeah. So 3 and 4 has to connect and 1 and 2 has to connect. So if these three, I mean, intentionally, the 3 has to logically connect with the 4 by using a physical connection. If it is not connected, we can say that is an open net. If one and 2 is connected in such a way, it is connected. Think that one more cell is interacting one. So if this has to be not connected with the 2 or 1. So if it is connected, that is called short. We should avoid opens and shorts while routing your all signal nets and optimize the data. So for another main criteria is you have to meet the timing. So you have to optimize the data path for the timing. So which you already know, data path means. Okay, now this is a flop and this is one more flop. Generally we used to discuss between only 2 flops. So this is a clock pin and this is a clock pin. This is called clock path. So the clock pin connected is called clock path and this is called data path. So data path somewhere here. So data path is like this. Clock to queue and this path. So you have to optimize data path. Nothing but if your data is not at all reaching before the clock, you have to add some buffers or you have to increase the drive strength to that is called data path logic optimization. And you have to check your DRCs and power. Quality of route should be present. Post route, nothing but after route. So if you are going to do some optimization, that is called post route, and post CTS will also exist. So after CTS, if you are going to optimize your CTS database, so that is called post CTS. And you have post placement, that no one call it as post placement. You can say that placement optimization. You have placement optimization, CTS, post CTS, route, post route. So you remember it depends upon your industry to industry. So where I'm working, so I have placement optimization, CTS, post CTS, route, post route. Okay, so these are inputs and the goals required for the routing. And coming to the pre-route checks, or you can call it as prerequisites for your routing. So first thing, all physical cells are, it's nothing but before to route, what you need to check. Before to route, you have to check whether all cells are placed properly or not. So all cells, nothing but all standard cells has been placed, and there should be physical cells, and it's the whatever the standard cells placed, and it should be optimized, and CTS has to be done, and CTS optimization should be completed. PG nets must be pre-routed. Physically, it should connect all macros and standard cells. I mean, not the power has to connect all macros and standard cells. There should not be any ideal nets. Ideal net, nothing but any floating nets. And the congestion should be tolerable, and the timing should be in limit. Okay, there should not be any unconnected pins. You had to, I mean, you had to check whether your design is routable or not. So there are a lot of logic sitting here, one in a lot of logic. So totally your design is occupied with the cells. So then you cannot route the design, nothing but you are unable to give proper connection to the design. For example, there is a room, it's occupies with I mean, the capacity of room should be 80, and a 20% should be route. If your capacity of your room is 100 people, so if 100 people sit, they cannot connect one to other. So that is called routability. You have to check the routability, and you have to check whether fan outs, high fan out nets are there or not. So I mean, if I mention a high fan out net as 20, so it should not be greater than that specified limit or specified value. So these are pre-route checks. Okay. Now, till now, I'm just saying width, height, pitch. You don't know, right, what is a width and what is a pitch. So if you see here, if you observe, this is one metal. Blue color indicates a metal. A wire, simply you're seeing a wire like a hat. This one, right? A cylindrical fashion wire in your home. So it is a wire. The width of the wire is called wire width. Okay, and between two wires, you think that there is a wire here and then one more wire. The spacing between, I mean, the separation between these two wires are called wire spacing. Think that there is one wire here and one wire. So that a gap between these two wires are called spacing. Okay, and pitch, what is a pitch? So think that this is one metal and this is one more metal. There is some central line here in the each metal. If you see, or just think that half of the metal and half of the metal, so the distance between this half to this half is called pitch, or first line of the metal to the next line of the metal is called pitch. Let me draw this one. This is called pitch. The metal first line and the second metal first line is called pitch. Or you can say the middle of the one metal and the middle of the another metal, or one end to another end. That is called pitch. Now don't confuse with width and pitch. Width is nothing but exactly the internal shape, or nothing but x-axis is called width. Spacing between two wires or gap between two wires are called wire spacing or space. Pitch is nothing but you are going to compare. If there is a center, there is a line like this, and there is one more metal like this. Okay, so the distance between or the gap between these two is called pitch. Hope you understand now. And coming to that via, I already said that. So each metal has to connect. I mean, if I say metal one has to connect with the metal 2. So these two metals are said to be connected through a term called via. So if you have metal 1, metal 2, there is via node. Metal 2, okay, let me draw with the red lines. So this is metal 1, and there is a metal 2, metal 3, metal 4. You may confuse. Metal 1, metal 2, metal 3, metal 4. You will have like this fashion. Okay, suppose now it is a metal 1, so you cannot route your cell I mean, there are, if there are two cells here, so one, there are will be routing tracks, which I explained already. So this cell has to connect to some point here. So first it will route with metal one. Metal one is a horizontal, or if it is a horizontal, next should be vertical. Vertical, metal 2. Then metal 3 will be some other thing, metal 3. And next, metal 4. Next, metal 5. Your connection will go like this. Okay. So if I say this is a metal 1, if I say this metal 2, so when it will get connected, because there should be a part called via. This is via 1. So here via 2. And metal 3 and metal 4 connected with via 4. Metal 4 and metal 5 via 4. Metal 5, metal 6 via 5. So these are called vias. So if two metals has to be connected, it has to connected by using via. So via width will be there, via spacing will be there. So generally, if you see, via structure looks like this. There is one metal. It is in like a square format only. Once you get a DB, I will show you. This is something that is a metal 1. This is a metal 2. Metal 1 and metal 2. So now how via looks. So via should enclose this area. I mean, simply you are tying something. So if you're tying two items, think that there is two broken items. The one is one metal one, thing that one other is metal two. So how you are going to tie? So you are going to keep some gum like a fevistick. So that fevistick which is connecting both is called a via. The same way. So two metals has to be connected by using some means like this. It's called as some enclosure. You can call it as a via enclosure. If you look here, the red color, it's a via. Okay. So each metal consisting, I mean, metal between two metals, you have one via. So we have to give a different name. So that's why via 1, via 2, via 3, via 4. If you have M10, M9 has M9 via. M9, M8 has M8 via. The same way, vice versa till M0. Okay. So this is via information and wire pitch, wire width, and wire spacing. Okay. So coming to the next part, now till now what we discussed nothing but what is a routing, what are the inputs required for the route, okay, and next what is the goals of route and prerequisites or simply some checks before route, and there is some routing constraints also. Okay, I didn't capture that one, but you just listen. So you before to the route, you had to, there is a specific file. Yesterday we discussed about clock specification file. So there is some files which are given to the input of your route. Okay, so for that, in that file, how to, you had to define some constraints. You had to constraints which layer you had to use. So generally till M0 cannot be used. If you will come to know once you are into industry. So when we are going to use M0, M1, M2, M3, that you will come to know. Okay, you have to give a layer number, layer name. Okay, and you had to set the maximum length. So now think that there is one cell here and one more cell here. This has to be logically and physically, these are logically connected. So you have to give a physical connection. So think that you are using M10 layer. So you should not use M10 continuously. Nothing but long metal length is not used. So how you have to go? Metal 1, metal 2, metal 3, metal 4, metal 5, metal 6, like this. Till metal 10, you have to connect this way. So the length, maximum length of the routing layer is also mentioned, and minimum width, minimum spacing, maximum width, maximum spacing, set preferred routing. So if I say metal 1 is horizontal and metal should be mostly vertical, HV fashion. I already said HV or VHVH fashion. So Now if I say metal one is generally M10, if you say M10 is horizontal, in some cases, so you can constrain this M10 as vertical, but you have to go for less routing. I mean, so it's M10 is defined as a horizontal routing. So M10 has to route horizontally only. But if you want to route a minimal distance, I mean, nothing but minimum length, so you can make M10 as vertical. So this is called a preferred routing direction. You can make non-default also. So that has to be come from your technology file. Okay, and you're constraining half grid. So generally, so there are your design is defined into grids. So if you see your home, so how the current they are going to I mean, they're going to give power in proper way. So randomly, if you see there are some points where you're getting a power. So when you close that one, I mean, during the construction, if you see that one, so they will indicate some tab points. Through that only it has to route. The same way, your design can be divided into some grid structure. So this on grid structure only you have to route. So, but for specific metal layers, when you go move to higher, so it can go for a half grid. So grid nothing but think that your design is divided into like these lines. So M1 has to route in this way. M1 has to route over this line only, this way. But when you go for the higher letters, so instead of line, you can just have, okay, let me try again. This is your block. Okay. So the routing grids with like horizontal lines and vertical lines also will be there. So these are all grids. You can call it as manufacturing grid. So when you turn on M1 metal layer grid will only turn, you can see. So that you can switch on, switch off your metals. There is a control panel here when you look into the tool. So when you switch on M1 grid looks like this. So you have to route metal in this way. So exactly it has to follow like this. So when you turn off, each layer has some color. So now metal 2 has to be routed in this way over the line like this. But when you go for the higher letter, you can instead of grid, you can go for half grid also. That also you can come to know. And you have to give the you have to give the way to route, and in specific locations or in critical cells, you can say this cell has to route. You can have some conditions. Don't use, don't touch. And you can define for some cells, so these cells has to be route only in M1 M2 M3, so it should not go higher layer. That also you can constrain. So these are routing constraints in your design. And coming to the route stages, each and every stage have some route engine. I mean, if I go for the route engine, so route engine will go 4 stages. First one is a global route, the second one is a track, third one is a detail route, and fourth one is a search and repair. For example, when you go for the placement, tool placement engine will go for the 4 steps which we already discussed. First, initially it plays randomly the cells, and then you are going for refined placement, then legalization, then you are going to modify, optimize that. The same way, route will also go for the 4 stage. One is a global, one is a track assignment, one is a detail route, and one is a search and repair. So we'll discuss tomorrow. Yeah, just I will show you. So these are called grids. If you see that, let me zoom. You're seeing, right, the boxes. So all these boxes are called grids. Okay. So on these grids, your route will go like this. Your route, this is one metal, another metal, another metal. If you see here, there is a source point and the destination point. So I will explain you what is the destination point and source point. Now, yeah. What a man. This is one cell. This cell is communicating to another two cells. There is one input is going, I mean, the output of this cell is going to input of some other cell, and the second output may go to another cell. So this is the source one, and these are the destination one. So this way tool will get route. Okay, can I stop till here or shall I go? Sai, Sham, please confirm. Okay, you understand at least little bit.
Go on Monday. Yeah, ma'am.
Okay, what about you, Sham? Sai? Okay, then maybe Sai. Oh, Saida? Saida is not there. Huh?